Welcome back. So in previous lecture we looked at mostly the deformation and compressional tectonic environment, and we saw a couple of surface expressions of faulting along the low angle reverse fault, or we can say thrust faults. Now one of the major topic which is left out is your strike slip faulting environment. So the major sites, if we take in terms of the plate boundary, where we see the strike slip motion or transform plate boundaries, so they are located, for example, here in the Mediterranean part region. You have close to Algeria, and then we have the transform plate boundary over here, and that is between the along the Himalayas, and this part is your Chaman fault system. We also have the strike slip which is taking place here. These are the major one, and the one of the most prominent we see between the Pacific plate and North American plate, that is your San Andreas fault system. So mostly what we see, the displacement is accommodated along a typical strike slip fault. If it is not oblique, then we will just see that the slip has taken place horizontally, displacing the landforms as well as the sediment succession here. So geomorphic markers associated with strike slip environment will see a couple of features, that is fault topography we see on the surface, and then we'll talk at later again in a similar way the trenching part. So major strike slip faults that have been assessed for paleoseismicity are typically associated with plate boundaries, and some of the most important that are what I was mentioning is between your North American and the Pacific plate. You have the San Andreas fault system, and few more in the Alpine fault system you have in New Zealand, that is between the Pacific and the Indian plates. Northern Anatolian fault between the Turkish and Eurasian plate, and the Dead Sea faults between African and the Arabian plate. And other active strike slip faults are located within major lithospheric plates and define the boundary of continental microplates like Central Asia, Mongolia and China. A final major class of faults as yet unstudied for paleoseismology is the numerous submarine transform faults, and that's what we see along the spreading centers. So conservative plate boundaries, transform faults at oceanic plate boundaries. We have the major one, mid-oceanic or mid-Atlantic ridge. Transform faults at continental plate boundaries we will see mostly in the basin and the ranges, and along the passive margins, like for example Bay of Biscay. Destructive plate boundaries with oblique convergence. So those were the conservative plate boundaries, and now we are having the strike slip environment along the destructive plate boundaries with oblique convergence. We see a transpression at continental plates boundaries like in New Zealand, California, Sumatra, Andaman. So we see this as an oblique convergence along this one. Okay. And then we have the constructive plate boundaries within oblique extension. So we have the back arc basins where also we will see the strike slip motion, and one is the Kuril archipelago, and then in the intraplate strike slip like intraplate regions where we see mainly in Asia, that is the northern side of the Indian plate, or you can say in the Eurasian plate we have the tectonic escape. Okay. And transtensional in the mid-Atlantic ridge area. So these are the few examples where you will be coming across mainly the strike slip motion of major and minor faults. Okay, so transform zones, mostly you will see the strike slip motion or the deformation in the mid spreading centers or the mid-Atlantic ridge, which is marked here. And we see also, like this is what has been shown, same, you have the strike slip motion along the fracture zone here. So you have the mid-oceanic ridge over here. So this, both the plates are moving, like it is moving in this direction here, and then this is moving away. So the motion is taking place along this one. So mid-oceanic ridge, so this portion is basically an inactive one, and this one is the active. Okay, so if we take this portion as a marker, then we see that this plate, this part of the plate is moving away from, because this is the spreading center. So this portion, if we take as an alone, then we clearly say this is an extensional which is taking place. So this part is moving away from one another. So you have this portion which marks the active transform fault, because this portion is moving away in this direction and this is moving in this direction here. So this portion is an inactive fracture, but this is an active, where the two plates are passing by each other or with respect to each other. So this photograph, which I have shown earlier also, which clearly shows the displacement on the surface, and if you take this boundaries as a marker here, then this portion has moved like that, and this portion has moved in this direction. So if you are standing here, then you will mark this as an left lateral strike slip fault. So two type of motions we have already discussed, so I'll just quickly move to the slides further ahead. So we have, like we see dextral movement, which we mark as an right lateral strike slip. Sinistral movement, we say that that is a left lateral strike slip, and that what we see here. So we have the sinistral one, you have the left lateral, so the left block is moving towards you. So if you are standing here and trying to view this, then this is left lateral and this is moving away, whereas this is right lateral dextral, which is moving towards your side. So right block is moving towards your side. So the surface manifestation already we have discussed. The most prominent one which we will see, the offset of streams, formation of linear valleys, and if you are having an oblique component, you will also see the formation of fault scarps. So this then, and one of the most prominent strike slip system on Earth between the Pacific plate and the North American plate, that is your San Andreas fault system. So this was during a 1960 San Francisco earthquake, and the features which you will come across will be formation of sag ponds, linear valleys, and offset of streams. So now, as we will move further in this lecture, we will talk about that how we are going to use the offset of streams, and in what condition you will be able to see the formation of sag ponds, and third one what we took was the pressure ridges. This part we have already covered, so I'll just move, but you can refresh this, keeping in mind that we will be looking at the sag ponds, then formation of the linear valleys. Okay, and if you are having the oblique, then slip, then you will have scarps formation, and we will also see the pressure ridges or shutter ridges here, and the most prominent one will be the offset of drainage. So this is an example of the Hayward fault, which shows creeping here. So this portion has moved here, and this one is over here. So fault runs somewhere here. So this portion is your typical right lateral. If you stand here and view, or you stand here and view, then it will be the same motion. So you have right lateral strike slip faulting along this fault. So as I discussed that we will come across like one number of faults, not a single fault line, and that forms the total. It will form the fault system, and this is for this San Andreas fault system. So I'll just quickly move this part. Already we have covered, but of course this is in the next slide. We will talk about the riddle fractures, how they are developed with respect to the fault which runs across this one. So usually in the fault zone we will be able to see the formation of the riddle structure on the surface. Okay, if the general movement, if we take like that. Okay, so we'll talk about this in the coming slides. That you have the deformation zone, okay, and you take the principal displacement zone, that is your fault, and if it shows the right lateral movement, then two definite type of deformation you will come across here. Okay, one is compression and another is extension, and two different sets of fractures will form, and they will have a typical angle with respect to one another. That is with respect to mainly the main fault zone or the displacement zone. One is it will be at low angle, okay, another will be at high angle, and so you have the compression in one direction and extension taking place in another direction. So this zone is marked by compression. So you will have synthetic strike slip faults or the riddle fractures which will develop having a low angle around ranging from 15 to 20 degrees with respect to your principal deformation zone, and another one will be your antithetic strike slip faults. So small fractures or shear fractures will form, and then this will be at high angle, which will be ranging from like 60 to 75 degrees with respect to the main fault zone. So this what we were able to pick up where the deformation is going on in a strike slip pattern and in along the Hayward's fault, that I'll try to explain. So now if we look at the different deformational features, prominent one usually will come across the formation of sag ponds and formation of pressure ridges. Now this will be two prominent landforms which you will see in a strike slip environment. Now how they are formed actually? So if you have the step overs, okay, right stepping or left stepping. So if you have the faults which are getting step over, it will result into the formation of either the restraining band or you will have the releasing band, and restraining will be your contractional compression and releasing is your extension. So suppose if you take this example which has been given here very clearly, but let us draw it and then see what exactly. So if you take this as a principal fault here and then step over to your left, so you are standing somewhere here and looking to the fault. Okay, so what see, so you have the fault running like that and then stepping to your left. Okay, so left stepping, and you have the movement which is taking place over here like that. Okay, so you have the right lateral movement. So right side is coming towards you, this is also moving away. So this portion is getting compressed, hence what you will see the formation of ridges. Similarly here, if you have the portion which is stepping to right. So right step over, this was left and this is the right step over. So this portion again you are having this portion is moving in this direction, this will move away from this like that. So then you will have in the overlap portion you will have the landform which will be formed will be your pull apart basin. And the same has been explained here. So you have the overlapping zone where the step over is taking place. You will have different form of deformation and different landforms associated with same type of movement. Okay. So this step over will result into different pattern of deformation. Either it will be like if you are having right step over, then you will have extension, left step over, you will have compression here. So this again explained here with the bend. So you are having the fault coming here, then stepping to your left. Okay. Then you are getting this one here, and then if you are having the right step over, then you are able to see the extension in this zone. So you have extension, you have contraction here. So this is what has been shown here. So you will have push up, that is your ridge, and this side you will have the basin. So if you have, for example, the left lateral, then the things will be exactly the same, but not the deformation will change. So if you change the deformation, just remember this, that the portion moving towards each other will result into compression, the portion moving away from each other will result into the formation of basin. So you have extensional and contractional features. Similarly, it has been shown here. So you will have again this is the right lateral. So you will have the step over here will result into different deformation pattern. So then typical of dextral slip. Now if you this portion we were talking about, now in case of first we'll talk this and then we'll get back to this one here on the top. So in case of right lateral, so what has been shown here, so you are having suppose you have the fault here and then you have the right stepping. So again we mark the arrows here, that it shows so both the arrows are moving away from one another. So the overlapping zone will have extension, and that what we have discussed. And similarly, if you are having this fault here and you have the portion here overlapping will have contraction. So we'll see folding, and this is your left step over, this is your right step over. Similarly, in case of the left lateral slip, okay, so this is we were looking at the right lateral. Now in similar case, if you are having left lateral and you have the left step over, then what you are going to see, so you have the fault here and then the step over is towards your left. Okay, so again we will put the arrows here, and this is your left lateral. So left lateral, so the left block is moving towards your side. Okay. So again this is in your direction. So this portion will have extension, that is the formation of sac ponds. Okay, and you will have elongated basins. Similarly here, so you have the fault, this one, and then it is right stepping. Okay, so again the movement is left lateral here on both the faults. So what we see, right stepping, so this portion is moving this side and opposite to this, so this will result into contraction. So we will see folding here, and this is in case of the right step over. So if you compare this, then if you are having left lateral right step, then you will see folding, right lateral right step, you will have extension, and exactly opposite what you will see here. So now if you look at the shear fractures with respect to the right lateral movement and the left lateral movement, and if you consider the ellipse, then you will have extension over like that and the contraction in this direction. So the movement what we see is the right lateral movement, and the shear fracture or riddle fractures we will be able to see in terms of the what we were talking about, the high angle and low angle with respect to the principal deformation zone. So if you are having the that is your synthetic one is your low angle, and the antithetic fractures will be at high angle. So what you are having is the left stepping you will see in case of your right lateral movement, and the folds you will be able to see in fashion of right stepping. So this, if you recall the chart, you will be able to understand it better. So in case of your left lateral, so again we'll have the ellipse here, so you will have extension in this direction and contraction in this direction, and exactly opposite you will be able to see, you will have the right stepping and echelon fractures, whereas the contraction you will see what you were looking at, the right stepping here, you will have left stepping here, and similarly the what you see the related features, okay, the folds or the thrust faults or the extensional normal faults. So these are few important aspects which you should remember when we are talking about the strike slip signatures of strike slip faulting. So what we were talking about is the formation of linear valley. Then we were talking about the, I'll just use another pen so it is clear. So stream offsets, okay. Then we're talking about, for example, so this we are taking as in right lateral. Okay. Then what you will see here, because this is your fault, you are having left stepping, so this portion is your moving here, and this portion is again like that. So you will see the formation of pressure ridge. Then suppose the fault is going like that, then again you have the deformation like this, then you will have formation of basin here. So these are few important landform indicators which will help you in demarcating the strike slip fault on the surface. Okay. So we can say this as in geomorphic markers. So this is the same thing which we were talking about the shear fractures. So you have right lateral again, so you will see the folds, so you will have folds right stepping, and this will be your left stepping. Again the thrust folds you will see right stepping, and if you overlap then you are having the folds which are right stepping here, and then you have the extensional one is your left stepping. So similar thing together. So if you have the right lateral, then what you will see is the pop-up or push-up here. So you have the formation of pressure ridge, whereas if you are having, so this will be your left stepping, this will be your right stepping, so you will have the formation of the basin here, and similarly which has been explained here, that you will have the formation of synthetic faults and you will have formation of antithetic faults here. And then this is what we are having. So if you take this, we have the synthetic faults. So we have compression in this direction, we have extension in this direction, and which will result into the formation of the extensional faults and the thrust faults exactly perpendicular to that. Okay. And if you look at this one, again the similar configuration, we have the right lateral strike slip, and if you have left step over, so you have fault running here and then jumping on this side, then you have the uplift or the pop-up, and if you are having the fault jumping to your left, then you have the extension, that is formation of the basin. Now if you look at this one, the fault runs over here, and we have the cracks or the shear fractures which are developed here. So we have the extensional crack over here, which is at high angle, and then we have the compressional cracks which are fractures which are developed almost at low angle with respect to the principal deformation zone or fault. So now coming to the other part here, what we see is that a clear deformation boundary in terms of Indian plate and the Eurasian plate. So not only will be able to see all in the compressional tectonic environment, will be able to see the thrust faults or the reverse faults, but also if you are having oblique collision or convergence, then you are going to see the formation of the strike slip faults or transform fault boundaries. Okay. So we have prominent transform fault boundary over here in the eastern side of the Indian plate, which shows your right lateral motion, and on the left, that is your western side, you have Cheman fault system which shows left lateral fault system, and this location we have, that is this shows all thrust faulting, and this is because of the Indian plate is just protruding or banging with respect to your Eurasian plate here. So this it shows. Along with that, what we have this one here, this is another fault system which is right lateral, is your Karakoram fault system, and many more in the Tibetan side of the Eurasian plate because of the lateral escape of this plate here. So in total, if you take the right lateral and left lateral strike slip faults, so we have this is Sagain fault system. So we have this plate boundary here, we have on the western side, and then few further north in the China side. So these are all because of the oblique convergence with respect to the different plates. Okay. So you have the same one here which we were talking about. So you have the Sagain fault system here, then the Karakoram one, and this is your Altendik fault in Tibetan side, and Kulun fault, again it is having, this is left lateral, this one is your again left lateral here, this one is right lateral, and then what we are looking at here is Cheman fault system and the Sagain fault. Sagain fault system is your right lateral and Cheman fault is your left lateral. So this is how it has been explained, that what is the reason for the formation of this fault system here as a right lateral, and this side, that is on the western side, is your left lateral. So suppose you take this portion as an Indian plate which is just banging into the Eurasian plate or the Tibetan plate, then this portion is what we see is escaping or has been pushed out towards southeast, and because of this contact here, since this portion is moving like that and this is coming out, so this is giving rise to your right lateral, and this portion is moving like that and this is coming out, this is giving rise to your left lateral. And then the other faulting which we see here as in Kulun fall or Altintek fault. So the tectonic extrusion or lateral escape hypothesis is explained with this. I'll stop here. Thank you so much.